Hello, everyone. So today we're going to hear from Josef Valvoda, who's a final year PhD student at Cambridge, advised by Simone Teufel and Ryan Cotterill. And Josef is primarily interested in legal NLP, but has also worked on a variety of other topics, including information theoretic approaches to NLP, and also on benchmarking compositionality with finite state machines, which is what he'll be talking about today. So Josef, take it away.
Thanks, Will. And thank you for having me. I'm glad I can open this year session. I saw a lot of the co-author that I actually worked on this paper have given talks, so I'm joining effectively the team, although so some of these names might be familiar. I'll be talking about the work on benchmarking compositionality with formal languages. Let's see if I can, there we go. Which is work with Naomi, which I saw gave a presentation, John, who's I think present, Adina, who might give in future, and Ryan, I think, who started last year, as I was looking through the list. So let's start about the work. So what are we benchmarking? Well, we are benchmarking neural networks, and we are benchmarking them because they are everywhere, and they are dominating the NLP venues. And not only that, they are dominating public imagination. I don't know about you, but my Christmas was spent talking with people about ChatGPT, which was new. No one ever asked me typically about what I do, but now they all vaguely have a sense what it might do with, because they've been reading about it. If this hype is justified at all, then maybe we should think about what we want our neural models to do, what kind of aspects of human cognition they should exhibit. And one popular aspect is compositionality. So let's talk about a little bit about why that might be desirable. Well, we want neural networks to generalize like humans, and they need to be reliable like people. They should ideally behave like people, more or less, and they should also perhaps require less data to train. Some have questions where it's possible from text alone, but here we'll kind of try to investigate the hypothesis that this is possible from text only. So what does compositionality mean? Well, in our work, we take a popular mathematical definition from Richard Montague, who is one of the most influential voices in formalizing the theory of natural language semantics, although he himself seemed to look down on the task quite a lot. He says that he sat down one day to do something he previously regarded and continued to regard as both rather easy and not very important, referring to the field I think many of you will be working in. So he's a man who uses quite strong language. Nonetheless, he did contribute in several papers some foundational work to the semantic formal semantics research. In particular, there are sort of two strains or two ideas from Montague that we'll be building on here. One is that there is no important theoretical difference between natural languages and the artificial languages of logicians. So I'll later come back to this because I'll be showing you how we sample artificial languages. But maybe more importantly for the compositionality, we go with Janssen's interpretation of Montague, which is that, in particular with regards to compositionality, which is that syntax is an algebra, semantics is an algebra, and meaning is a homomorphism between them. Okay, we'll come back to homomorphism. Don't worry too much. We'll get to it. But first, let's talk about kind of what we set out to do in the paper. So there are a lot of handcrafted compositionality data sets. A popular one is one of the popular ones is Scan language by Lake and Baroni, which has had many follow-ups since. The way the experimentation works is that, or the language works is that you have some sort of natural language commands like jump, and you are translating them or trying to learn a function that will map them onto these entirely different meaning commands like capitalized jump. And then jump left can become L-turn jump, and turn left twice can become L-turn. So this is what scan roughly looks like. And handcrafted datasets are great for many reasons. I mean, they are built from ground up for a specific task. The linguists that create them have complete control over their content, and they are designed to capture exactly what we want to study. But they also have downsides. They are time-consuming to create. They only provide results over one single example of an entire class of languages. And they make it very hard to attribute learnability to some precise aspect of a language. And these are the limitations that we try to address in our work a little. So handcrafting is tedious. Let's automate it. But in order to do that, we need a formalism first. A formalism that's mathematically well studied, is provably learnable, is familiar to NLP practitioners, and ideally could generalize previous work on compositionality. So it should capture scan language. Okay, before we find the formalism, let's go a little bit back to Montague. So according to Montague, compositionality is a homomorphism. So what is homomorphism? Well, it's quite simple. Homomorphism is a structure-preserving function, but we'll talk a little bit more about the formal definition, so we are on the same page. So what do we mean by structure? In the structure-preserving, well, we mean a monoidal structure. So let's start there. What is a monoidal structure? What the heck is a monoid? Well, monoid is a simple algebraic structure. And the formal definition of monoid is a set A equipped with an operator, your bullet, with the following three properties. It is closed under the operator. So AB in set A and also a bullet operator B also remains in set A. So it says closure, there's associativity. It doesn't matter whether you put the brackets here, and I don't know if you can see my mouse, but between the A, B, or between the B and C, and has unique identity element, so that A plus this element or operator element is equal to element operator A, and both are equal to A. So it's sort of this empty element aspect. So these are the three requirements for a monoid. Let's get an example of this. So the free monoid, a simple monoid, let A be clean closure of an alphabet sigma. And let's consider an alphabet containing two elements, A and B. Then the clean closure of that alphabet with string concatenation, which is the operator, forms the free monoid. And empty string is the identity element. So we can now check whether this structure would satisfy our definition of a monoid. Well, there's a closure, concatenation of A and B still is within the clean closure of A, B. There's associativity. It doesn't matter which order you concatenate with. You will always come up with the same string. And if you have the identity element, then you satisfy all three of these requirements for the free monoid. Okay, so now we can go into the homomorphism. So now you know what monoid is. Monoid homomorphism is has simple two definitions. So it's a function between A, which is a monoid with the bullet operator, and B, another monoid with bullet operator. And the homomorphism occurs if you have a function where inserting the identity element to the function returns the identity element, and the function applied on the X operator y is equal to the function applied to x and y independently, and with the operator, let's say, concatenating them together. So it's fairly simple. Now, in order to get to what we are doing, what we are sampling, now we have to relate that to the subsequential finite state transducers, which is what we work with. So let's talk about that for a bit. So in order to connect Montague with our work, we need to define a subsequential finite state transducer. I'm sure many of you not all be more familiar with this than I am, but just to make sure that we are on the same page with respect to notation, let's go through it quickly. So a finite state transducer has an input alphabet sigma, an output alphabet theta, q, a finite set of states, lowercase q, a start state, f, a set of final states, and a transduction relation between the input alphabet and the output alphabet. An example of it is here on the right. So we have a input alphabet, which is AB, an output alphabet, which is AB as well. We have one state, which is both the initial and final state, start and final state. And we have this transduction relation where inputting A will return B, or inputting B will return A. So you can read it basically from left to right. Now, subsequential just simply means that with respect to the input tape, the transducer is deterministic. Okay, so let's see. Is the question now is whether homomorphism between two free monoid can be encoded by one state SFST. So this very simple SFST, whether it satisfies homomorphism. And it turns out it satisfies it. So we can check that. We can have a look at all the states or all the combinations possible. And we can say if they satisfy the two requirements of homomorphism. So we can see that the first requirement is satisfied. And we can also see that the second requirement, FAB, so if you have a look here, FAB will return BA, is the same as concatenating FA and FB. So FA returns B and FB returns A. So BA equals BA. But not all as well, as some unsettling news. If we extend the SFSTs to two states, then they suddenly are no longer homomorphism, at least not in a straightforward manner. And you can see that if we do FAA, so we start always with 0, so AA, so that would be BA as an output. And if we compare that to FA and FA, so we go 1, that's B, and we can start from the beginning, 0 to 1, that's B. BA doesn't equal BB, and therefore the multistate SFST is not a straightforward homomorphism. So how do we resolve this? Well, we can do something quite simple. We can lift the monoid in a matrix to incorporate the states into values. So we can represent the operation FA as a matrix multiplication over strings or string concatenation. Now, what's the concatenation is fairly straightforward, but what is interesting here is that we sort of denote as 0 the annihilator, that is sort of situation within the matrix where multiplication will give you still 0. There's no concatenation there because it's an impossible state to get into. But otherwise, it's straightforward matrix multiplication. So we can now represent FA as a multiplication of these two matrices and get this matrix representation on the right. How does that help us? Well, we can also represent FAA as a matrix. You can see that we can start in the state 0 to 0, which would be 1, 2. So that's BA as an output, and fill the matrix like this. That's how we transform a SFST into this matrix representation. And now we have a solution. It is a homomorphism after all, in this very sort of specific sense. SFSTs are homomorphism. This holds for larger ones as well. And we can double check this by looking at FAA being BA00AB, and FA, we have seen before that if we have 2 of them, we get exactly the same answers. So FAA equals FA. And therefore, we have this homomorphism. Okay, so why did we go through all of this? What was the purpose? Well, we can now go back to evaluating neural networks. So we have these downsides of handcrafted datasets. First, the manually annotated datasets are time-consuming to create. Well, we can now begin to sample datasets. So if we know that these homomorphisms are contained or captured by SFSTs, we can generate and sample from SFSTs to create dataset instantly. And that's exactly what we're going to do. We can also, so the second problem, results are only over a single example of the entire class of languages. Well, we can now sample over the entire class of languages, because we can take certain type of relations. In our case, with the SFSTs, it's subregular relations, and we can do experimentations over that whole class of languages. And finally, it's hard to attribute learnability to some precise aspect of a language. Well, we know that those SFSTs have quite precise definition of their components, and we can modulate those, right? We can set the number of states, we can set the size of alphabet, we can constrain them in different ways, and then observe how those aspects correlate with performance of neural networks. So that's exactly what we did. We have generated 2,800 unique SFSTs. And for each of them, we generate datasets of input-output string pairs, which look a lot like those scan sequences that you've seen before, except now we are following Montague again with the assertion that there is no difference between real and artificial language. So ours is completely artificial. It's just numbers that form our alphabets. And we each dataset contains 20 to 40,000 unique input-output pairs, which we split onto train, test, 80-20 split. And we have released the code with the tools for you to generate datasets, so you can play around with it. There are many different things you might want to do with it. We kind of stuck to modulating the number of states primarily, but there are of course other aspects that you could play with. And then with these datasets, well, we train a LSTM over those datasets. Okay. Is that neurally generated Schmidt-Huber picture? No, that is a real Schmidt-Huber picture, I'm afraid. It's a good question. Yeah, he does look unreal in that picture, though. So what did we find? We found minimum transition coverage of 400 samples. So this is our sort of bound on learnability. So what is a transition coverage? It means that moving from, let's say, 0 to 1, this is a transition. So you have to move 400 times in the data set. You have to have sample of that 400 times in order for the network to learn it. And it's soft bound. So if we increase the size of the network, we get, well, in this case, smoother and slightly less pronounced drop-off. But either way, we found that in between 20 and 40 states, size of the SFST, the dataset becomes unlearnable. The SFST become unlearnable. And we can push that a little bit back and forth with increasing or decreasing the size of the LSTM. Okay, so let's go a little bit back to scan now. So we have found this threshold, how does it apply to scan? Well, we can cast scan as an SFST. In fact, that was kind of the impetus of this work. We thought, well, scan is a finite language. It can be represented by an SFST. Here's a small part of scan represented by an SFST. So you have your states from 0 to 10. This is just a small block of only a small part of the language with respect to the command jump. There's an equivalent block for every other command, and then the language is a bit larger. So in reality, scan is massive. It's got 7,728 states in our estimate. And what's worse, the minimum transition coverage limit is broken by scan. So the 400 examples per transition that we think are required for learning an SFST, it doesn't hold here because scan is perfectly learnable, but it's much, much larger than our largest SFSTs, and the coverage over transitions there is therefore much, much smaller. So what gives? Well, we think our theory for this is that there's some sort of native complexity that because scan is not generated by a random SFST, but rather by grammar, the native complexity that we discovered, which is of SFSTs, i.e. their size, their intuitive complexity, is not really doing justice to scan, because you have to change scan to fit it to SFST. You have to kind of really go out of the way to capture grammar, such as scans, in sort of the format of SFSTs, and because we can see that the native complexity metric of SFSTs is learnable completely by neural networks, but the complexity metric of native complexity of scan goes beyond it. We hypothesize that the neural networks that we consider, at least, their native complexity is not that of SFST. It is likely to be higher up the Chomsky hierarchy. So what next? Well, we think that future work should seek automata whose native complexity metric can consistently predict the learnability of arbitrary language tasks. So we advocate for this move up Chomsky hierarchy. What would that mean? Well, if you look at, for example, those blocks that are naturally created in the scan language, those blocks that represent, I showed you jump, but equivalent one can be seen for, let's say, walk or turn or whatever it might be, the other commands. If we could find a formalism that perhaps can account for them, perhaps a push-down automaton, then, or a transducer, then we could perhaps start to get at the question of closer to the question of what is the native complexity metric for neural networks. And we hope to work that in the future on that. And I think that's it. Thank you, and yeah, I hope that you have plenty of questions, because it was a quite short rundown.